CERN has quietly begun probing an atomic anomaly so strange, so unexpected that it could force us to rewrite the laws of physics as we know them. What if this isn't just a glitch in the data, but the first flicker of a dark force lurking beneath our reality? Based on emerging research and speculative theoretical models, the world's leading particle physicists are wrestling with results that don't fit any known framework. By the end of this video, you'll understand why this anomaly, still unconfirmed, still highly speculative, could be the seed of a scientific revolution. From the first millisecond, it's clear this isn't the usual CERN announcement about incremental improvements or safety upgrades. Within weeks of a new run at the Large Hadron Collider, data streams began to diverge subtly from expectations. What started as a curiosity in the tracking systems turned into an undeniable pattern. Certain particle collisions were producing decay products with energy distributions that refused to match the predictions of the standard model. These differences weren't tiny statistical wiggles. They were waves crashing against the bedrock of modern physics. In laboratories around the LHC ring, teams cross-checked detectors, recalibrated magnet currents, and even swapped out sensors. Yet each time the anomaly reappeared, the energy spectrum of these decay products seemed to hint at an interaction that shouldn't exist, one that tugged on atomic nuclei with a force not accounted for in any chart of fundamental interactions. Early simulation runs designed to reproduce standard model events repeatedly failed to capture this extra pole. Scientists tentatively labeled it X1, a placeholder name for what might become the first new force in decades. But they were clear. These findings are preliminary and steeped in speculative data. No definitive claims have been made, and the scientific community remains cautiously skeptical. But what comes next changes everything. If this kind of mind-blowing science excites you, make sure to subscribe. We dive into discoveries like this every week. To understand why this anomaly matters, you need context. CERN's LHC is famous for melding protons at near-light speed to reveal nature's smallest components. In 2012, it delivered the Higgs boson. Since then, our models have held firm, yet every so often, nature seems to slip us a puzzle piece that doesn't fit. These latest results originate from a new collision dataset aimed at probing heavy quark interactions. The teams originally envisioned refining measurements of rare B-meson decays. Instead, they stumbled on something that could precede an unknown fundamental interaction, tentatively dubbed the dark force. The experimental setup is robust, with overlapping detectors, multiple cross-check algorithms, and independent analysis groups in France, Switzerland, and beyond. Still, none can conclusively rule out unknown systematic errors. What makes this search different is the persistence of the anomaly across runs and detector configurations. That repetition elevates this from an outlier to a genuine mystery. If these emerging hints prove real, they could open the door to physics that unifies gravity with quantum theory, or even to portals connecting to hidden dimensions. What do you think this means? Comment before we dive deeper. Around the world, theorists are racing to interpret X1. One camp suggests it's evidence of a fifth fundamental force, alongside gravity, electromagnetism, and the strong and weak nuclear forces. If so, this force would likely operate over subatomic distances but with a strength comparable to the weak force. It could manifest through a new gauge boson, sometimes nicknamed the dark photon. Other models propose that X1 arises from interactions with a hidden sector of particles, a shadow realm only detectable through its influence on ordinary matter. Speculative though they are, these theories serve a critical purpose. They generate testable predictions. If a dark photon is involved, it may leave signatures in other experiments, like beam dump facilities or precision atomic spectroscopy. Some researchers are even exploring tabletop experiments with ultra-cold atoms to look for minute forces that conventional theory cannot explain. It's a thrilling moment. The anomaly has galvanized physicists across disciplines, from collider experts to condensed matter physicists, all trying to corner this elusive dark force. And then, nothing prepared scientists for what happened next. In the latest round of collider runs, researchers attempted a new trigger strategy, focusing on events where the energy imbalance was maximal. The idea was to amplify any effect of X1. Astonishingly, the anomaly intensified. Rather than a slight deviation, the data now showed consistent energy deficits. Particles seemed to lose energy to something invisible when protons collided. A fraction of the expected decay energy simply vanished. It wasn't absorbed by known particles. It was siphoned off into the unknown. This twist suggests the dark force might act as a channel, allowing particles to bleed energy into a hidden sector. It's as if our detectors are watching ghosts. We see where energy should go, but it disappears before it arrives. The implications are profound. If true, this could explain why we observe only a fraction of the universe's mass and energy in visible matter. The rest, dark matter and dark energy, could be tied to this hidden interaction. But be clear, this is still speculative, emerging research. No one has yet traced the missing energy directly. We infer its existence from the gap in our measurements. That's where things get strange. Scientists have responded with both excitement and caution. Some call for new runs with different collision energies to see if the effect persists. Others argue for alternative explanations. Maybe the detectors are miscounting neutrinos, or cosmic rays are sneaking into the data. Yet the consistency across multiple experiments strengthens the case for a genuine anomaly. If this dark force is real, it could be the first non-gravitational window into the dark sector of the cosmos. If you've made it this far, you're clearly into the deep stuff. Hit like and let us know your theory in the comments. Simulation, higher dimensions, or something else? In the quieter corridors of theoretical physics, where the most profound and speculative ideas are born, a deeper and more speculative debate is unfolding. What if the dark force we're detecting isn't just a force at all, but the very manifestation of something far more profound, something related to hidden dimensions? This idea is rooted in the fabric of string theory, a framework that suggests the universe we observe is just a small slice of a much grander reality. In this model, space itself is made up of more than just the three spatial dimensions we can perceive. There are potentially many additional spatial dimensions curled up so tightly that we cannot directly observe them. The theory posits that these extra dimensions could harbor fields or forces beyond our current understanding. If this is true, our experiments might only be catching a glimpse of these hidden realms, a shadow, if you will, of a far more complex underlying structure. The energy we're seeing disappear in particle collisions might not be lost at all. Instead, it could be leaking into a higher dimensional space beyond the reach of our detectors. The behavior of these particles could reflect the interaction with a field that is somehow connected to or embedded within these extra dimensions, but is too subtle to detect directly with our current technology. Alternatively, some scientists propose that this strange force doesn't arise from extra dimensions, but from something even more fundamental: quantum fluctuations in space-time itself. This hypothesis draws on ideas from quantum gravity, a still-emerging field that seeks to reconcile the laws of quantum mechanics with general relativity. In quantum gravity, space-time isn't just a passive stage where events unfold. It's a dynamic entity that fluctuates and shifts at the smallest scales. If this force is tied to quantum fluctuations in space-time, it could imply that what we think of as empty space isn't empty at all. It could be teeming with energy fields and interactions that we're only beginning to uncover. These speculations are not just academic musings. They represent some of the most exciting and high-stakes ideas in modern theoretical physics. To even entertain these possibilities requires us to rethink our entire understanding of the universe. Imagine, for a moment, that every particle we smash together in a collider experiment isn't just interacting with the known forces but is also leaking tiny amounts of its energy into an unseen higher dimensional space over microscopic distances. This might seem negligible, but over cosmic scales, that small energy leakage could explain some of the most perplexing phenomena in the universe. Take, for example, the mystery of dark matter. We know that galaxies rotate at speeds that cannot be explained by the visible matter alone. There has to be some unseen mass exerting a gravitational pull. Could this missing mass be the result of interactions with a higher dimensional force that we're only now beginning to detect? And what about dark energy, the mysterious force accelerating the expansion of the universe? Could the same dark force be responsible for both the cosmic acceleration and the energy loss we're observing in particle collisions? Then there's the bizarre behavior of quantum entanglement. In entanglement, particles become linked in such a way that their properties are instantaneously correlated, no matter how far apart they are. This strange connection has puzzled physicists for decades, leading some to speculate that there could be hidden dimensions or forces at work that allow for instantaneous communication across vast distances. If our dark force is connected to these quantum phenomena, it might be the key to understanding the seemingly paradoxical nature of quantum mechanics itself. It's a beautiful unification of the forces of nature, if it's real. If this dark force is truly responsible for some of the most profound mysteries of the universe, it would suggest that the distinctions we've made between gravity, electromagnetism, and quantum mechanics are merely approximations, incomplete reflections of a deeper, more unified reality. Theoretical physicists have long sought such a unification, one that merges the macrocosmic realm of general relativity with the microscopic world of quantum mechanics. Could this dark force be the key that unlocks this long-sought connection? But right now, it remains a tantalizing hypothesis. We're still in the early stages of understanding the nature of this anomaly, with only a handful of anomalous data points to guide us. The models are speculative, the interpretations preliminary, and the experimental verification still elusive. However, these are the seeds of a paradigm shift, one that could, over time, revolutionize our understanding of the universe. For now, the idea that every particle collision might reveal hidden dimensions or that quantum fluctuations in spacetime could be shaping the cosmos remains a breathtaking possibility, waiting to be confirmed or refuted in future experiments. This is the beauty and challenge of science. Each discovery opens up new questions, each answer leads to more mysteries, and each theory pushes the boundaries of what we can imagine. While we can't yet say whether these speculations will stand the test of time, they provide us with a new lens through which to view the universe. A lens that might one day help us understand the fundamental forces that govern everything from the smallest subatomic particles to the vast expanding cosmos. But what you're about to hear next will stretch your imagination further than you ever thought possible. After months of intensive data crunching, a specialized cohort of CERN physicists reached out to colleagues in astrophysics. Late-night video calls bridged the Geneva labs and observatories scattered across the globe. On one side, collider experts were refining their missing energy measurements. On the other, astrophysicists were combing through petabytes of telescope and detector records. Their target, elusive anomalies hiding in the cosmic microwave background radiation, the ancient afterglow of the Big Bang, mapped in exquisite detail by missions like Planck. Tiny temperature fluctuations on the order of millionths of a degree didn't quite fit the standard cosmological model. Could these minute blemishes be the cosmic fingerprint of the same dark force tugging on particles inside the LHC? Simultaneously, teams analyzing gamma-ray data from the Fermilab LAT satellite found unexplained excesses in galaxy clusters, such as Perseus and Coma. These clusters should emit gamma rays at predictable rates through known processes like cosmic ray collisions. Yet there was a persistent surplus at energies of a few GeV. In the depths of Antarctica, the IceCube Neutrino Observatory was recording sporadic bursts of high-energy neutrinos, particles so ghostly they passed through light-years of lead unscathed. Individually, each signal could be chalked up to astrophysical quirks. Together, they painted a pattern too consistent to ignore. When the teams overlaid the collider's missing energy profile with the energy spectra from gamma rays and neutrinos, a remarkable convergence emerged. The energy deficits and excesses lined up in both scale and shape. Statistical analyses showed correlations at the 3 sigma to 4 sigma level. Far from definitive proof, but enough to send shock waves through both communities. The culmination was a joint CERN Space Observatory paper titled Possible Common Origin of LHC Missing Energy Anomaly and Astrophysical Excesses. Using advanced Monte Carlo simulations, the authors demonstrated that a hypothetical dark force mediator, akin to a dark photon with a mass in the tens of MeV range, could simultaneously siphon energy from proton collisions and subtly alter cosmic scale processes. Their unified model mapped this mediator's coupling constants to both quark interactions in the LHC and photon-neutrino propagation across intergalactic space. It wasn't a smoking gun discovery, far from it, but it was the first cohesive framework suggesting that the same unseen force might be at play in lab experiments and the cosmos alike. If further experiments confirm these early findings, we could be on the verge of uniting particle physics and astrophysics under a single dark umbrella. And yet, Every major theoretical advance faces rigorous scrutiny. Rival groups have already noted that the apparent cosmic signatures, those subtle distortions in gamma-ray maps or minute temperature fluctuations in the cosmic microwave background, could stem from more prosaic astrophysical processes, such as previously uncharted pulsar populations or complex plasma interactions in galaxy clusters. Equally, within the LHC data itself, there remains the possibility of an overlooked systematic effect, perhaps an unmodeled detector inefficiency or an unaccounted for neutrino background, is masquerading as missing energy. That is precisely how science advances, by challenging extraordinary claims with the highest standards of evidence. Only through independent replication, cross-laboratory analyses, and new collision runs with alternative trigger schemes can the community either validate or refute this tantalizing unified model. Until then, the idea of a dark force weaving together quantum phenomena and cosmic puzzles remains an electrifying, but provisional hypothesis. Let's retrace our steps. We began at the LHC, where an unexpected pattern surfaced, particles seeming to bleed energy into an unseen realm. From there, we explored theoretical proposals. Dark photons mediating a fifth force, hidden dimensions siphoning quantum effects, and the speculative framework linking laboratory anomalies to astrophysical excesses. Each layer of theory brought us closer to a possible new window on the universe, yet each demanded its own experimental proof. Along the way, we saw how diverse fields, from collider physics to precision spectroscopy in high-energy astrophysics, converge in the hunt for this anomaly. What started as a curious blip in a detector has blossomed into a cross-disciplinary quest, uniting physicists in the search for a force that could finally bridge the divide between the quantum and the cosmic. Looking forward, the next chapter will be written in data. Upcoming LHC runs with upgraded detectors, dedicated beam dump experiments, and novel tabletop setups in atomic physics will put the dark force hypothesis to the test. Meanwhile, next-generation space telescopes and neutrino observatories will probe the cosmos for complementary signatures. Should these efforts converge on consistent results, textbooks will need rewriting. Gravity, electromagnetism, and the nuclear forces will no longer stand alone. Instead, they'll form part of a richer tapestry, threaded through by this mysterious interaction. Even if the anomaly dissolves under scrutiny, the process will sharpen our instruments, refine our models, and deepen our understanding of how to interrogate nature's subtlest secrets. Whatever the outcome, this journey from atomic collisions to cosmic curiosities underscores the most profound truth of science. Each question answered births new mysteries, and every anomaly is an invitation to explore reality at its most fundamental level. As researchers continue to probe this anomaly, several critical factors will need to be addressed before it can be classified as a true breakthrough. 1. Reproducibility of results. One of the cornerstones of scientific discovery is whether results can be reproduced consistently across different teams, experiments, and setups. The fact that this anomaly has been observed across various detectors and configurations at CERN is promising, but further experimentation with different parameters, like energy levels, collision types, and particle beams, will be necessary to confirm the initial findings. If the anomaly holds up under these conditions, it will become increasingly difficult to dismiss as a systematic error or misinterpretation of the data. 2. Unification of forces. This anomaly might hold the key to unifying the known forces of nature. Currently, we have 4 fundamental forces. Gravity, the force that governs large-scale objects like planets, stars, and galaxies. Electromagnetism, responsible for electric and magnetic fields, and the interactions of charged particles. The strong nuclear force, the force that holds atomic nuclei together. The weak nuclear force, involved in radioactive decay and other subatomic processes. But physicists have long sought a theory that links them all. This anomaly could be the first glimpse of that unified theory. If the dark force discovered at CERN is indeed a 5th fundamental force, it could be the key to understanding quantum gravity, something that has eluded scientists for decades. 3. The role of hidden dimensions. The idea of hidden dimensions is especially tantalizing. String theory, one of the leading theories in modern physics, posits that there are extra dimensions of space that are curled up so tightly that we can't observe them directly. These dimensions might influence the behavior of particles, potentially explaining anomalies like the one CERN is detecting. If energy is leaking into these dimensions, it could be revealing a side of the universe we can't yet detect with current technology. 4. Dark matter and dark energy. One of the most exciting implications is that this dark force could help explain some of the greatest mysteries in astrophysics. Dark matter and dark energy. We know that galaxies and other large cosmic structures behave in ways that can't be explained by the visible matter alone. Dark matter is theorized to be a form of matter that doesn't emit light or interact with electromagnetic forces, but it exerts gravitational effects. Similarly, dark energy is believed to be driving the accelerated expansion of the universe. If the dark force discovered at CERN is real, it could be responsible for these cosmic phenomena. Perhaps dark matter isn't simply invisible. It might be interacting with normal matter through this hidden force. Dark energy, which causes the acceleration of the universe's expansion, might also be related to this new force in ways that could revolutionize our understanding of the universe. 5. Cosmic connections. The idea that data from the Large Hadron Collider (LHC) and data from astrophysical observations, such as gamma rays and neutrinos, could be linked is mind-boggling. The cross-correlation between LHC experiments and cosmic observations suggests that the same unknown force might be at play at both the microscopic and the cosmic scales. This connection between the quantum world of particle collisions and the vast scale of the universe is a powerful idea, which would represent the unification of physics in a way we've only dreamed about. 6. Future experiments and theoretical models. While the theories are speculative, the next few years of experimentation will be crucial. CERN's future runs, as well as dedicated experiments in neutrino observatories and even space telescopes, could provide further evidence or dismiss this hypothesis altogether. The idea of running simulations and building experiments to detect dark photons or other signatures of this dark force is incredibly exciting. The search for the dark force isn't just about answering one question. It could open the door to dozens of new research areas in both theoretical and experimental physics. As you can see, this discovery isn't just another anomaly. It's a potential door to a profound new chapter in our understanding of the universe. It could be the first steps toward explaining the very origins of the universe itself, how the forces of nature work together, and how we fit into the grand, mysterious cosmos. Conclusion. In the end, the search for this dark force is a perfect illustration of how science works, through curiosity, skepticism, and rigorous testing. Every discovery sparks new questions, and every answer uncovers even more profound mysteries. Whether or not this anomaly represents a true breakthrough in physics, the search for answers will undoubtedly lead to a richer, deeper understanding of the universe. If you're fascinated by these kinds of mysteries, keep an eye on future updates from CERN as they continue their investigation. The questions they are asking could very well shape the future of science and our understanding of reality itself.